Uber handles over 10 million trips daily, with peak QPS exceeding 5,000. A mere 100 milliliters latency increase can drop conversion by 7%. Today, we're reverse engineering the architecture that powers this real-time transportation network. By the end of this video, you'll know how to design a ride-sharing platform capable of matching riders and drivers efficiently, even at massive scale. We'll see how those 10 million trips impact our design choices. We'll also explore how algorithms like A-search could be applied for optimized routing. We'll also discuss common mistakes candidates make, like neglecting real-time updates. Did you know that Uber uses sophisticated algorithms to optimize routes and dispatch drivers, reducing wait times and improving efficiency? First, let's nail down the requirements. Functionally, we need rider-driver matching, real-time location updates, trip management, and payment processing. Non-functional requirements? High availability is critical. Aim for 99.99% uptime. Low latency is also key, especially for location updates and dispatch. Scalability? We need to handle millions of concurrent users and growing trip volumes. Let's clarify. Do we support carpooling? What about different vehicle types? We'll focus on standard rides to keep things manageable. An interviewer might ask, what about surge pricing? We'll assume that's a future enhancement. We also need to consider security and data privacy regulations like GDPR. A common mistake is not clarifying the scope up front. We also need to consider the legal and compliance aspects of operating in different regions. Let's crunch some numbers. Assume 1 million daily active users, DAU. If each user requests a ride twice a day, that's 2 million ride requests. Assuming peak hours account for 20% of requests, we get 2 manelma, 0.2, let's see, 3,600 seconds, somewhat 11 QPS. For driver location updates, assuming each driver sends updates every 5 seconds, and we have 100,000 drivers, that's 100,000, 20,000 QPS. Storage? If we store trip history for 3 years, with each trip record being 1 KB, that's 2 mil, 365. 1 KB, 2 tub. Bandwidth? Real-time location data will dominate. We'll revisit this after the HLD. These estimations will guide our architecture choices. We'll also need to estimate the number of concurrent connections to our WebSocket servers for real-time updates. Pause here and think. How would these numbers change if we supported carpooling? What about internationalization? Here's the high-level architecture. We'll separate read and write paths for optimization. Clients, riders and drivers, interact through mobile apps. The write path handles ride requests and location updates. The read path handles fetching nearby drivers and trip details. We'll use a load balancer to distribute traffic to API gateways, which handle authentication and rate limiting. The core logic resides in microservices, a matching service, a trip management service, and a payment service. Asynchronous tasks like analytics are handled via message queues. We use a rate limiter because we want to prevent abuse and ensure fair usage of our resources. We'll use Nginx as our load balancer because it's battle-tested and provides excellent performance. The API gateway will use Kong because it offers plugins for authentication, rate limiting, and request transformation. A common mistake is not separating read and write paths, leading to performance bottlenecks. We also need a rules engine to handle surge pricing and promotions. Let's dive into the core matching logic. The key is finding the nearest available drivers in real time. A naive approach would be to calculate the distance between the rider and every driver, which is own, not scalable. Instead, we'll use geohashing. We divide the map into a grid of cells, and drivers are associated with a cell. When a rider requests a ride, we search the rider's cell and neighboring cells for available drivers. This reduces the search space significantly. We might be tempted to use a simple radius-based search, but geohashing provides better indexing and scalability. The core service needs to be idempotent. If a request is retried due to a network issue, it shouldn't create duplicate trips. We use geohashing because it allows us to quickly narrow down the search space for nearby drivers. An interviewer might ask, what if the rider is near a cell boundary? We can search multiple neighboring cells to handle that edge case. We can use the S2 geometry library for more precise geohashing. It uses hierarchical space-filling curves to divide the Earth's surface into cells. Remember those 5,000 peak QPS? Geohashing is critical to meeting that demand. Another algorithm to consider is the Hungarian algorithm for optimal assignment of drivers to riders, especially in high-demand scenarios. However, its complexity makes it less suitable for real-time applications compared to geohashing. For the data model, we'll use a combination of relational and NoSQL databases. PostgreSQL is suitable for trip details, user profiles, and payment information, where ACI'd properties are important. For real-time location data, we'll use Redis. Its in-memory data store provides low-latency reads and writes. We rejected Cassandra here because the data volume for location data isn't massive, and Redis's simplicity is a win. We'll index location data using geospatial indexes to speed up nearest neighbor queries. We use Redis because its in-memory nature provides the low latency required for real-time location updates. We'll use PostGIS, a PostgreSQL extension, for geospatial queries on trip data. A common mistake is using only one type of database for all data. We also need to consider data partitioning strategies for PostgreSQL to handle large volumes of trip data. To handle the massive scale, we need caching, replication, and sharding. We'll use Redis as a cache-side cache for frequently accessed data, like user profiles and trip details. Database replication ensures high availability. If the primary database fails, we can fail over to a replica. For sharding, we can shard the trip data based on region or driver ID. This distributes the load across multiple databases. For static content like map tiles, we'll use a CDN to reduce latency and bandwidth costs. Remember the 20,000 QPS for driver location updates? We can reduce the load on our systems by implementing a rate limiter to prevent abuse and optimize bandwidth. We use sharding because it allows us to horizontally scale our database to handle the increasing volume of trip data. An experienced interviewer will probe what happens when a region becomes a hotspot. We can reshard based on a smaller geographical area or use consistent hashing. Consistent hashing, like the Katama algorithm, ensures minimal key redistribution when nodes are added or removed. Pause here and think, what other scaling strategies could we use? We could also explore using a message queue like Kafka for asynchronous communication between services, improving resilience and scalability. Remember the 10 million trips daily. Sharding is crucial to handling that volume. For fault tolerance, we'll use redundancy at every level. Multiple load balancers, API gateways, and application servers. If one component fails, the others can take over. We'll implement circuit breakers to prevent cascading failures. Monitoring is crucial. We'll track key metrics like request latency, error rates, and resource utilization. We'll set up alerts to notify us of any anomalies. For example, if the average response time for the matching service exceeds 200 millers, we'll trigger an alert. This proactive approach helps us identify and resolve issues before they impact users. We use circuit breakers because they prevent cascading failures and improve the overall resilience of the system. We can use Hystrix or Resilience4j for implementing circuit breakers. A common mistake is not having proper monitoring and alerting in place. We also need to implement proper logging and tracing to diagnose issues quickly. We've designed a ride-sharing platform capable of handling millions of users and trips daily. The key trade-off is latency versus cost. Geohashing improves matching speed, but requires additional indexing. Caching reduces latency, but increases complexity. Next steps, we could explore more advanced matching algorithms, dynamic pricing, and carpooling features. Remember the 10 million trips daily? This architecture is designed to handle that scale, and we've addressed the latency concerns. We could also explore using machine learning for fraud detection and demand forecasting. We also need to consider the ethical implications of using algorithms to optimize ride-sharing, ensuring fairness and transparency.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.